Hello, APChem. I'm going to finish up the chapter 8 of the Zumdahl textbook on bonding. This is the various aspects of the advanced discussion of the localized electron bonding model. We call it the LEM, or the localized electron bonding model. It's a molecule. It says that a molecule is composed of atoms bound together by sharing pairs of electrons, and that they use their atomic orbitals to hold those bound atoms together. In this model, we tend to pair up the electrons and try to locate them geometrically around the atom in a particular geometry or a set of bond angles or positions that will help us understand the shape of the molecule. So some terms here, we have lone pairs, which are electrons that belong to only one atom, so they are localized or positioned on a single atom. And then we have bonding pairs, which are electrons found in the spaces between the atoms. So these are the ones that are shared. So we distinguish between lone pairs that are not used in bonding or non-bonding electrons and bonding electron pairs. The three main aspects of the localized electron bonding model, two of which we'll get into in this video, are Lewis structures, valence shell electron pair repulsion, and hybridization. So today we're going to talk about drawing Lewis structures, even for some of the more advanced examples, and also how to determine the shape of a molecule using valence shell electron pair repulsion. We'll save hybridization for Chapter 9. Gilbert Lewis developed the system for putting bonds and unshared pairs on pictures that involve the element symbols. In other words, just our shorthand that we use for drawing chemical bonds as lines and dots as unshared pairs. The three basic steps for writing Lewis structures are to, number one, make sure you know exactly how many valence electrons you have in your molecule or set of atoms. And then number two, use pairs of electrons to form the bonds between each pair of bound atoms. And then number three, arrange the remaining electrons to satisfy the duet rule for hydrogen and the octet rule for any second row element. Sometimes that involves using double bonds and triple bonds. And sometimes you can just use single bonds for making sure that everybody has their duet or octet. Lewis structures can also be used to show ionic bonding, as you see in the lower left-hand corner. We see the magnesium and the chlorines with their dot structures, or their Lewis dot structures, and the transfer of electrons from the magnesium atom to the two chlorine atoms to make them chloride ions. And then the magnesium becomes +2 and the Cl's become -1, and they end up attracting in a crystal to make magnesium chloride. So these are a very useful way of looking at electrons in atoms, is to draw the element symbols and to put dots between them. As you see below, we have H2 with its duet. NH3 is used as an example of an easy example here for writing a Lewis structure. First, you sum up all the valence electrons in the atom, 5 for nitrogen, and 1 times 3 for the 3 hydrogens is 8 valence electrons. First, you bind the nitrogen and hydrogens together. This particular picture uses dots. I might have used lines between the nitrogen and hydrogens. A line is two shared electrons, a pair of shared electrons. The three single bonds between the nitrogen and the 3 hydrogen, which allow them to be stuck together, use up 6 of the 8 electrons. That leaves you with 2. If you put the extra 2 electrons as a lone pair on nitrogen, nitrogen has an octet, or nitrogen is surrounded by 8 electrons, and hydrogen has a duet, or hydrogen is surrounded by 2 electrons each. Here we see some Lewis structures for some other common molecules and ions. In the case of water, you would add up the valence electrons. 6 for oxygen, 2 for the 2 hydrogens is 8. You would draw the O, and you would branch off the 2 hydrogens with single bonds. You had 8 valence electrons, you used 2, so that leaves you with 4. Those 4 electrons are best placed on the oxygen. You can't double bond because hydrogen only gets a duet. You place them on the oxygen as unshared pairs, giving oxygen an octet and hydrogen a duet. In the case of carbon dioxide, CO2 on the right here, carbon dioxide has 4 valence electrons for the carbon and 6 for each oxygen for a total of 16 valence electrons. I would start out here with single bonds between the carbon and the oxygens. That would use up 4 of the 16 and leave me with 12. Then I would ask myself, what is the best way to place the 12 electrons? If I place 6 on each oxygen, that does not leave carbon with an octet. It only has 4. If I place 4 on each oxygen, and as in the form of 2 pairs or 2 unshared pairs, and then use the other 4 electrons on each side to make double bonds, you see that this picture actually gives every atom an octet. It takes care of bonding the carbons to the oxygens, and it's a good structure that uses 16 electrons. Cn minus shows us what we would do for an ion, cyanide ion, Cn minus. Carbon would bring 4 valence electrons and nitrogen would bring 5 for a total of 9. However, the -1 charge is another valence electron for a total of 10. So Cn minus has 10 valence electrons. The best way to arrange them, you can try different structures, but the best way to arrange them to give carbon and nitrogen both an octet is a triple bond and 2 unshared pairs, 1 on each atom. Unfortunately, there are many problems with the Lewis structure approach. In other words, this model needs multiple patches in order to represent nature well. One thing that we tend to find for bonding is when we look at beryllium, beryllium typically does not surround itself with 8 electrons. In other words, it doesn't have an octet. It's what we call octet deficient. Beryllium typically bonds by having 4 electrons or 2 shared pairs. So down below we see BeCl2. This is an exception to the octet rule, and you just need to remember that beryllium will make 2 bonds and not 4 bonds. Likewise, boron is another one that's going to be octet deficient. Boron typically will make 3 bonds, not 4. And BF3 is an example where boron is attached to 3 fluorines with single bonds and has 6 electrons surrounding it, but doesn't attempt to double bond or anything in order to get 8. So those are 2 exceptions you need to remember. One thing about BF3 is that since it is octet deficient, it actually can bond to something like NH3 by using the 2 electrons on nitrogen to make a 4th bond. So here we see NH3 attaching to BF3. This would not be possible, we don't believe, if boron had an unshared pair or had a double bond, because nitrogen wouldn't be able to bring more electrons into boron's sphere and give it an octet. So this is a special type of bonding where one molecule donates both electrons in the pair, in the bonding pair, to the other atom. On the right side, we see a couple of molecules that appear to have an expanded octet. Now first, just a few comments about the octet rule. You can always expect carbon, nitrogen, oxygen, and fluorine to obey the octet rule. Boron and beryllium will tend to do 3 pairs and 2 pairs. And the second row elements cannot go over 8 because the second energy level has 2s and 2p, which can only hold 8 electrons. However, when you get to the third row and heavier, you can actually satisfy the octet rule or exceed the octet rule, because the third row elements have d orbitals with space in them. And so by using d orbitals, we can actually expand the octet rule for the third row and heavier. So here on the right we see SF4, where the sulfur is surrounded by 5 pairs of electrons or 10 electrons, but it is allowed because sulfur is a third row element. Also, SF6 has sulfur with 6 single bonds for a total of 12 electrons surrounding the sulfur, and that is also allowed because sulfur can expand the octet rule because it is third row or below. Try interactive example 8.7. One other patch that we sometimes put on the Lewis structure model is when more than one valid Lewis structure is possible. An example of this is nitrate, NO3 1. In NO3 1, as you see in the lower left, you get a double bond for one of the O's and 2 single bonds to the other O's. However, another valid Lewis structure would be to simply place the double bond attaching a different O, and another one would be attaching to the third oxygen. So the question is, where does the double bond go? All 3 oxygens are equivalent locations for the double bond, so which one does it appear on? The fact is, it actually appears, according to measurements, to be averaged out over those 3 locations. In other words, instead of being a double and 2 single bonds, you actually get 3 1 1/3 bonds. The NO bonds are all equal in length and stronger than a single bond. So the best way to represent this graphically, or using Lewis structures, is to draw all 3 structures with a double-headed arrow between them, showing that there are 3 structures and that the 3 structures should be combined in order to understand the best electron structure for that molecule. I want to be clear here, the molecule does not switch back and forth between these structures. The molecule is at all times an average of the 3 structures. Example 8.9 helps you with drawing Lewis structures for resonance. Another problem that we sometimes run into is the case of odd electron molecules. When you have an odd electron molecules, it's always going to be awkward to make a Lewis structure, because the Lewis structure can't have pairs everywhere. It has to have a single, and so there's going to be some atom that's going to end up with a different number than 8 electrons on it, because some atom's going to have an odd number of electrons on it. In the case of odd electron molecules, the best approach is to use formal charge to determine the best structure. Formal charge is a calculation that's made by starting with the number of valence electrons on a single free atom and then subtracting 1 for every bond attached to that atom and 2 for every lone pair. So for example, in the lower left we see NO, and in the left structure, N has the dot for the single electron that's not in a pair, and N only has 7 electrons attached to it, so it's octet deficient by 1. On the right, we say, well, why not we put the octet deficient dot on the oxygen and let O have 7 valence electrons. One of these 2 structures is dominant, and we can determine which one it is based on formal charges. If we determine the formal charges on the left, the N is going to be 5 valence electrons minus 2 bonds is 3, minus the unshared electrons, which is 3, and so the nitrogen would be 0. Likewise, the oxygen would be 6 valence electrons minus 2 for the shared pairs or bonds, minus 4 for the lone pairs, and that would give oxygen a 0 formal charge. So in the bottom left-hand picture, the N and the O would both have 0 formal charge. In the right-hand picture, where the dot is on the O, the unpaired dot or unpaired electron, Nitrogen would have 5 minus 2 minus 4, or a -1 formal charge, and oxygen would be 6 minus 2 minus 3, or a +1 formal charge. So which is best, 0, 0 or -1 +1? Our goal would be we want to achieve formal charges as close to 0. If we do need to have a formal charge on a structure, we would prefer any negative formal charges reside on the more electronegative element. So if we look at this question, which of the two structures is dominant, the first NO structure is dominant because all atoms have 0 formal charge. So A, B, C, D, I would pick A for this multiple choice question. NO2 is another example. If you do the formal charges, you would find in the NO2 structure in the upper right down below there, the oxygen on the left is 6 minus 1 minus 6, which would be -1. The oxygen on the right is 0, and the nitrogen is 5 minus 3 minus 1, which is +1. Here we allow for this to be -1, +1, and not 0, because oxygen is the more electronegative element. And you really can't improve on this without giving a positive formal charge to oxygen if you were to place the dot on single dot on oxygen. Okay, sulfate. Sulfate is interesting. If you just try to do the Lewis structure for sulfate, sulfate has a -2 charge, and you do the 6 for sulfur and the 6 times 4, 24 for oxygen. You end up with 32 electrons, which you find is perfect for surrounding sulfur with an octet and oxygen with an octet, as you see in the bottom right. So it looks like sulfate should be an octet all the way around. However, if you do the formal charges, you find out the formal charges are quite messy. All the oxygens are -1 and the sulfur is +2. A possible better arrangement for this would be 2 double bonds and 2 singles. Remember, sulfur can expand the octet. If we do that, the single bonded oxygens will be -1, and the double bonded oxygens and sulfur will all be 0 formal charge. This is a more preferred structure, the one with 2 double bonds. Of course, there would also be some resonance structures for that as well. All right, now that we have the basics down for drawing the Lewis structure, how do we apply the Lewis structure to determine the molecular shape? The approach is called valence shell electron pair repulsion. Unfortunately, pair is a bit misleading because it can actually be 2 pairs if it's a double bond, or 3 pairs for a triple bond. So I prefer valence shell electron set, or maybe electron domain repulsion. Basically, we determine our molecular shape by minimizing the electron repulsions between the bonded atoms and the unshared pairs. So the first example of VSEPR shapes would be a linear molecule. In this case, the 3 atoms would be all in a straight line. We see this structure with BeCl2, and we also see it with carbon dioxide. In BeCl2, the beryllium has 2 single bonds. They would want to get as far apart as possible to minimize repulsion. So BeCl2 would have a 180-degree bond angle and would be linear. Carbon dioxide has 2 double bonds attached to the carbon. Those 2 double bonds would also spread themselves out in a linear fashion. We move up to 3 electron domains. When you have 3 things around the center atom, they arrange themselves to get as far apart as possible in a trigonal planar geometry. An example of trigonal planar geometry would be carbonate. Carbonate has carbon double bonded to oxygen and single bonded to 2 other oxygens. Of course, it would have 3 resonance structures, just like nitrate did in a previous slide. However, you would still have 3 sets of electrons attached to the center carbon. So we go to our center carbon and say how many sets of electrons, how many electron domains are surrounding the central carbon. In this case, three. Three things would spread out trigonoplanar. You'd have a 120-degree bond angle between the carbon and the three bonded oxygens. If one of the three electron domains is an unshared pair, then we have a subset of trigonoplanar, which is called bent. Ozone is an example of this. Ozone has two resonance structures, but it has oxygen bonded to two oxygen atoms, and then the center oxygen also has an unshared pair. We would expect approximately 120-degree bond angle for O3 in its bent structure. However, it's a little bit less than that, more like 116 degrees, because of the unshared pair that is repelling the shared pairs to make a bent structure. We move up to 4 sets of valence electrons, and we have tetrahedral. 109.5 degree bond angle. CH4 is a classic example of that. NH3 is another one, except that it has one unshared pair as one of the 4 sets of electrons. Because of the extra repulsion of an unshared pair, NH3 has slightly less than 109.5 degree bond angle. It has a 107 degree bond angle. Water would have a 104.5 degree bond angle, as it has 4 sets of electrons, 2 unshared pairs and 2 shared pairs, but it has a basic tetrahedral shape, but a little bit of distortion due to the unpaired or unshared electrons taking up a little extra space. When we move into expanded octets, we see that if we have 5 sets of electrons, we have trigonal bipyramidal. Trigonal bipyramidal has the structure that is shown on the left side there for PF5. It has a mixture of bond angles, 90-degree bond angles between the equator and pole positions. We see the 3 fluorines in the equator positions and the 2 fluorine at the top and bottom as polar positions. Within the equator positions, there's 120-degree bond angles. PF5 has 5 single bonds and no unshared pairs on phosphorus, so it has classic trigonal bipyramidal structure. SF4 has enough electron sets to be trigonal bipyramidal, but one of the electron pairs on sulfur is an unshared pair, and so SF4 will be a version of trigonal bipyramidal called sawhorse. ClF3 has 2 unshared pairs. We always put the unshared pairs in the equator positions because there's actually a little more space there, and they do need more space because they're more repulsive. ClF3 is going to be T-shaped and have bond angles of 90 degrees. XEF2, xenon difluoride, has 3 unshared pairs, and so those will all occupy equator positions, leaving XEF2 to be linear. I3- is another example of linear, just like XEF2. Finally, we have the 6 sets of electrons that we see in an octahedral shape, and SF6 is a classic example of a shape we call octahedral. ClF3 has octahedral geometry, except for one of the positions is an unshared pair. ClF3 is called square pyramid. In XEF4, we have 2 unshared pairs and 6 sets of electrons around the center. The unshared pairs will go as far apart as possible. They will be at the pole positions, and XEF4 will be called square planar.